All right. So welcome to this talk about crypto. We have a narrow room for a narrow topic, so that's good. That's a good start. What I'm going to show you today is some of the ways that we can use crypto wrong, and I'm going to show you that because it's important and because people tend to do lots of crazy stuff with crypto, and it's harder than you might think. So with crypto, I mean cryptography, not crypto coins. So no bitcoins or anything in this talk. Sorry if that's why you came. My name is Erlend. I am from a company called Blank in Oslo in Norway. I work as a developer on my day job, but I also do security testing and recently starting doing some bug bounty hunting as well. I'm also the creator and maintainer of Retire.js, if you ever use that, and I'm head of the OS Norway chapter as well. And I'm not a crypto expert. I'm a developer. Crypto experts, they are a different breed, and they know a lot about this stuff, a lot more about this stuff than I do. But I thought I'd bring some of the stuff that I found during both security tests and research to you guys, and then hopefully you can learn some from it. So why are we using crypto? Well, basically for confidentiality, that's the most common part. Like we want to protect something, we don't want anyone else to be able to read it. We might also use it for authentication or integrity. We want to protect something or show that this is the same thing that I sent. I'm the provider of this content. But we don't necessarily need to have both confidentiality and integrity. Like we could sign a token, and that could be a public token, but it's signed by us, so we provide integrity as a part of it, and we can use that for identification. Bruce Schneier is a wise man, and he said that anyone from the most clueless amateur to the best cryptographer can create an algorithm that he himself can't break, and this is important. Never ever invent your own crypto. It's going to go bad. Like proper cryptographers, they will create an algorithm, and then they will send it to all their fellow researchers, and they will break it, and then it'll go back and forth until they have something that works. And for most of us, that means that we should never even try. Some words I'm going to use, sorry about the wall of text, but some words I am going to use here that we need I'm going to use them, so I need to explain them first. Plain text, that's the data we want to encrypt. Ciphertext, that's the encrypted data. The key is, of course, the key that we use to encrypt it or sign it. An IV, or an initialization vector, that's something we use as a random start value at some times. A nonce is a random value to be used only once. Symmetric and asymmetric encryption, that depends on whether we're using the same key for both encryption and decryption, or if we have a public-private key system, and the same thing holds for symmetric and asymmetric signing. And then we have hashing. People tend to get these things wrong. When we see these breaches in the papers, people say, well, we had encrypted the passwords in the breach. Well, most of the time they actually hashed them and not encrypted them. And then we have encoding, which is not encryption, but sometimes people tend to think that they've invented something clever. If we go back to the early or the late 1800s, August Kirchhoff, he said that a crypto system should be secure even if everything about the system except the key is public knowledge. So that kind of tells us that we need to have a key for something to be a crypto system. If there is no key, it's probably an encoding. So that's also a way that you can figure that out. So the first important part when we're using crypto is to always have a secure, cryptographically secure random generator. And this is something that goes wrong from time to time. So a couple of examples. This is from some researchers that were looking into self-encrypting hard drives. And they found some bugs in some of these drives. One example, one of them had a 32-byte key. But it turned out that the 32-byte key was just a 4-byte key repeated 8 times, which means instead of the 32-byte key, you had a 32-bit key, which is a very, very big difference when it comes to keys. Another one was someone doing a survey on or research into what kind of public keys that they could find online, and they found that 5.56% of all TLS hosts and 9.6% of all SSH hosts had public keys that had either insufficient randomness or they were device default keys, which also tells us we have a problem with the stuff that we're putting online. Some other researchers were looking at Wi-Fi routers, and they found that the only seed that was taken into the randomness was the MAC address of the device itself. So you could basically, from the MAC address, you could calculate the Wi-Fi password, which is not what you want. Don't ever use like system random or like the normal random function that's provided by the framework. There's easy ways to break it. This is just one way of breaking it with something called Untwister, which you can find on GitHub. There are also ways where you can reverse engineer the state of the random function basically by looking at a small set of random values from the generator. This is what we often think when it comes to security. So instead of breaking the actual crypto, someone can try to grab the key somewhere. And where is the key? Well, it's of course on GitHub. So this is from HackerOne, bug bounty platform, and someone found a secret key on the GitHub repo of GratiPay, which is one of the companies hosting a bug bounty on HackerOne. And so we should never actually put our keys in source code. And this is more recent. 400,000 websites vulnerable through exposed Git directories. So people will they're going to deploy their new website and they accidentally include the Git directory, and so you have all the history of the Git repo on the website itself. And of course, if there are keys in there, people will find them. So they are constantly monitoring things like GitHub and all other repos out there and looking for keys. So over to encryption. So we now have a cryptographically secure key. It's generated in a proper way, and we want to start doing encryption. So we're going to start out easy. We're going to start out with a definition. So given a ciphertext, it should be impossible to find the plain text. So only the people with the key should be able to figure out what the plain text was. And the way people used to do this was with what we call one-time pads, which were just basically these big notes that you would pass around, or large rolls of paper that you could pass around, and you could use that to encrypt stuff. Of course, we're using computers now, so we're not using the paper-based ones, but we can generate a random key, and we can XOR the plain text with the key and get a ciphertext. And the decryption is the same thing. We just XOR it with the ciphertext instead, and we get the plain text back. This is quite easy. So if we have a message, and these are the bytes of that message, then we have a generated random key, and we get the cipher by just XORing them together. And of course, XOR is just, we do it bit by bit. So if we have the uppercase A and a lowercase a, and we XOR them together, we actually get the space character, because that's the only different one between the two. So that's actually also an easy way to transfer between upper and lowercase, by the way. We have some math here as well, like if we're using XOR. If we XOR something with a 0, we get the same thing back. If we XOR something with itself, we get a 0. People using assembly, they're used to this stuff. If like the order of the parts here, they don't really matter. So we can have these large things like this. We have A XORed with C, XORed with A XORed with B. Then we can switch them around. So we get A XORed with A, which is, as we see on the second there, it's 0. And then so the A just goes away basically, and we're stuck with B XORed with C. And we'll see why this is important in a second. So the one-time pad, it's very secure for a single message, confidentiality-wise. But we can only use the key once, which is kind of annoying for a crypto key. We can only use it once. And how do we exchange this key? The key also has to be at least as long as the message we want to send. So now if we want to pass a message, we now have the problem of passing the key, which is basically the same problem as passing the message. But we can of course meet up front and exchange this XOR key at some point and then use it later. But the reason why we can use this key only once is if we have one ciphertext that's XORed with this key and another one, and we XOR them together, we get the same A XOR with B and A XOR with C. Like the key falls away, and we're stuck with the plain text XOR together. So even if we don't know the plain text, we can now get the XOR of the plain text. So if we have enough plain texts, this actually allows us to figure out what the contents are. And if we know a single plain text, we can XOR the ciphertext with the plaintext and we get the key. So the system is kind of broken in a way. We can only use it once. And the reason why the message length has to be smaller than or equal to the key is if not, we'd have to wrap the key, and then we essentially get the same problem that we had earlier, where if we XOR the parts together, we get the plaintext XOR together. So an example of something using XOR, this was NQ Vault. This was, it had over 10 million downloads from the Android App Store, and it was supposed to encrypt your images and videos and everything. But someone was looking into this app and figure out what it was actually doing, and it, to start with, it only encrypted the first 128 bytes of each file. So if this was a video file, like the rest of the file was not encrypted, and it says encrypted in quotes here, because what they did was the key was basically the password, and then they did the hash code function on the password, and then they basically truncated it down to 1 byte. So there are only 256 different keys. This is trivially brute forceable. So we're gonna improve on this, and we're gonna try to improve our definition here. So given ciphertext, it should be impossible to find the plaintext, and we want to have a reusable key. So knowing a plaintext shouldn't reveal the key, and also we want to be able to encrypt stuff that's larger than the key. So basically, we have 2 types of ciphers. We have stream ciphers and block ciphers, and a stream cipher, we kind of stretch out the key. We have a generator that generates a key stream from a key. And we basically just XOR it together, just like we did with a normal one-time pad. One example of such a cipher is RC4, but that's not something you should use anymore because it's considered broken. But at least now we can have plaintext lengths that are larger than the key size. But this accidentally also leaks the plaintext length. So if this is a table of votes, we can clearly see who voted yes or no in this case, because one of them is shorter than the other. So we could have padded them, and then that wouldn't happen. But even if we kind of individually encrypt them with 1 key for each, we can still see that the third one is shorter than the other. So we would have to pad to avoid this problem of leaking the plaintext length. So we'll move on to block ciphers. What we do with block ciphers is basically we split the data into blocks of a given size, and then we encrypt each block separately. And the most common way we do this is with AES. Some people still use DES, and they should stop doing that because it's also considered broken. So the easiest way to do this is to take the plaintext that we have and use something called ECB. So we have the plaintext, we have the encryption function, we split the plaintext into blocks. We pad the last block because it needs to be at the same length as the block size, and then we encrypt each of these by running them through the encryption function, and out comes the ciphertext. And then at some point later we want to decrypt it, so once again we split it into blocks, we run it through the decryption function, and out comes the plaintext. And then we have to remove the padding, and there's our plaintext. This thing has a problem though, and that's AES, for instance, is a deterministic algorithm. So if we have the same key and the same data, the same block is going to pop out at the other end. And this is very well presented with this picture. Like we've encrypted a picture, but we can still see what the picture is all about because of the repeated blocks. So we have something called cipher block chaining. And with cipher block chaining, we're going to introduce noise into the encryption. This is kind of like using a salt when you're hashing passwords. So we start out the same way. We split into blocks, and we pad the last blocks to make it the same size as the block size. And then we add this initialization vector, which is noise. And then what we do is we XOR the IV with the first block of plaintext before we encrypt it. So now we've introduced some noise. So by selecting a random IV each time, we will ensure that we get a different plaintext, even though, or a different ciphertext, even though we encrypt the same plaintext. For the next block, we're going to use the previous ciphertext block as the IV. So we make a copy of that, we XOR them together, and run them through, and we keep going like this. And now we have the ciphertext. And we have to include the IV, because to decrypt this, you have to have the IV. And what we normally do then is just put it in front of the larger text. So when we want to decrypt it, we split it into blocks again. We run it through the decryption function, and then we do the XOR. And this is after the decryption function, and this is something we're going to see might be a bit of a problem. So then we take we use the previous ciphertext block as the IV for the next block, etc., and we go through this like this. Remove the padding, and we have our plaintext back. So if we want to attack CBC, so on this slide we have the I's at the left side of the screen, that's the IV, and the C's at the right side of the screen, that's the ciphertext. And then we have our decryption function, and when we run the ciphertext through the decryption function, we get an intermediate value, which is then XORed with the IV, which goes outside of the decryption function, and we get our plaintext. Now, if we were to modify a single bit up there in the ciphertext, that would completely garble the intermediate value, which is then XORed with the IV, and we would get a completely garbled plaintext. So we can't really mess with anything up there. However, if we were to change a single bit up there in the IV, it's going to pass outside the decryption function, and so we're only going to change a single bit down there. And now we're seeing that there might be a kind of an issue here. We can mess with the IV, and then that allows us to mess with the plaintext. So if the plaintext was a JSON token like this, and we have a user ID here, user ID 5, we could bring out our old XOR math here, and we know that a 5, that has the hex value of 35, which means that I11 and XORed with V11 becomes a 5. So it goes through the decryption function, we bring in the ID, and it becomes a 5. What we want is for this to become a 1, because the user ID 1 is usually the admin. So we want to become the admin. So we have to calculate some kind of new I11, which XORed with V11 would give us a 1 there instead of a 5. And the way we do this, we can just XOR it with the stuff that it was, which is 35, which is the 5, and then we XOR it with the thing that we want, because if we XOR with 35, it's going to become a 0, and then we XOR with 31, it's going to become a 31. So we can actually, by manipulating the IV, we can manipulate what was encrypted here without knowing the key. And this can be kind of useful for us. So we change this one, and we end up changing this one. So just to show you an example of this, here we have a tiny little application where we can download a paper. And the URL here is really small, so I'm just going to copy it out for you. It looks something like this. So we have a file name here, and we have a signature here. And this looks a lot like something that's encrypted. So what we're going to do is we're going to basically align the file name with the IV. Because what we want to do is we want to change this URL so we can download paper 2 instead of paper 1. But if we just try to change the URL and set it to paper 2, we're going to get invalid signature. So we need to somehow mess with this signature. So what we're going to do then is we're going to take this A9 here, and we're going to change it so that the end result would become a 2 instead of a 1. So we can just easily do that by just taking so A9 XORed with, so you can see I've done this before. We're going to change it from a 1 to a 2, and we need to get this back into hex format at the end. So the value we want instead of the A9 is AA. So we just go up to the signature and change from A9 to AA, and we get the second paper. So we kind of broke this by just messing around with the IV. So encryption is not signing. Encryption doesn't give us integrity. It only gives us some kind of confidentiality. When we're padding things can go wrong as well. Like there are a lot of ways that we can pad. We could pad with zeros, we could pad with random values, or we could pad with something called PKCS7, I mean. And this is a very common padding. And what we do then is basically we add padding bytes that where each byte is the number of padding bytes. So if we need to add 7 bytes, all the padding bytes will have the number 7 in them. If we need to add 6 padding bytes, all of them have the number 6 or the value 6. And the reason why we're doing this is that makes it easier to remove them later. So we can check them and see how many of these padding bytes are we supposed to remove. And that's harder if you pad them with zeros, if we pad them with random values. But now we know how many of them we should remove. As you can see on the last part here, if we have a message that's exactly at the block size, we need to add an entire padding block, because if not, if this P7 in this case was accidentally a 1, it would be removed, and it wasn't supposed to be removed in this case, so we need to add a full block of padding. But what happens if the padding is wrong? Like in this case, it says 3, but the 2 next padding bytes, they're not 3s, they're a 10 and a 5. This seems wrong. Well, what the programming languages will usually do then is to throw an exception. So in Java, you'll get a bad padding exception. In C#, you'll get a cryptographic exception with padding is invalid and cannot be removed. And in HTTP, you're usually, like if this is a generic application, you'll usually get a 500 because very rarely the developers have thought of this case. And this is actually enough for us to decrypt the data, which is kind of strange. And I'm going to show you why. So if we send in any of these blocks, we're going to get a correct padding. But the last block here, if we send in that, we're going to get a padding error, because likely this is not going to be one of the correct blocks here. So we bring back we have a ciphertext and we have an IV, and we don't know the plain text and we don't know the intermediate value. What we first do is we take a copy of the IV, copy it down here, and then we randomize the IV up here. This is going to create a padding error. So if we send this text at the top here to the server, it's going to respond with a 500, most likely. It's going to respond with a padding error. What we're going to do then is we're going to take the least or the rightmost byte of the IV, and we're going to try all values from 0 to 255. And at some point, we're going to hit a valid padding. So we start out and we try different values. And already at 3, we found a valid padding, which probably now means that we found a block which has a 1 as the in the plaintext. And now we can figure out what the intermediate value was, and we can figure out what the original padding was down here, because we can just XOR them together to figure that out. And then we go ahead and we change this to a 2 by changing the IV up there. And then we try the next byte. So we kind of break them one at a time. So now we have a 2 there, and we try the second rightmost byte of the IV, and we try all values from 0 to 255, like this. So we're going to spin it up. And then at some point, we're going to hit a valid padding where we get 2, 2. And then we change them by changing the IV to 3. And then we kind of, by doing this, we can break the message 1 byte at a time, starting from the end and going to the left. And this is what happens in movies, right? Where they're kind of figuring out one part of the password at the time. This actually works that way, and it's kind of strange. So I'm speeding it up now, and you can see like it's breaking this by sending messages. So at the left side of the screen now, you can see how many messages I would have to send to break this ciphertext. And I had to send 2,087 requests in this case. And per byte, I had to send an average of 131 requests. But still, I could steal the plain. I could figure out the plain text, and I could do this for multiple blocks. It doesn't have to be just one block. I could just do one block at a time. So by doing this, we can decrypt a ciphertext by using a padding oracle. And this was actually a bug in .NET back in the day. In 2010, they had this issue with something called Reb Resource AXD, which was often used for Ajax stuff. So there was a padding oracle in there, which you could then use to download like the web config, for instance, which was kind of bad. We've also had this problem in OpenSSL many times. So Poodle is one example. Poodle means padding oracle on downgraded legacy encryption. So we have the padding oracle in there. And there's been others as well, like Lucky 13 and similar ones. This is one I found on HackerOne. Once again, this is from Fabricator, which is used by Facebook. So there was a padding oracle in there. And how do we stop this? Well, we could try to catch this exception, right? We could try to. We're gonna stop it by catching this exception, and we're gonna return the same error as if, let's say, we were able to decrypt it, but it was not what we expected. So in this case, we're going to do we're going to try to decrypt it, and if it throws a padding exception, we're going to return not found. And also, we're going to do a database lookup if we were able to decrypt it and see. And if we find it in a database, we're going to return OK. And if not, we're going to return not found. So in this case, we're trying to be smart, and we're going to return not found regardless of if it was a padding exception or if it was just not found in the database. The problem here is very likely the database lookup is going to take time. So there's a side channel here. If it jumps from the decryption and down to the catch block, that's going to go faster than actually doing the database lookup. So there's a side channel. And we often have all kinds of side channels in these systems. So it could be computation and response time. It could be CPU usage if you're on a VM. It could be power consumption. It could be electromagnetic fields. It could be the size. We've seen examples of that, and a lot of other types of side channels. And of course, if it's a timing side channel, it has to be measurable. Like if this is over the internet, there's a lot of jitter and stuff going on, so it would have to be measurable, but sometimes it is. I found this example as well, which I found to be quite scary. By measuring the target's electromagnetic emanations, the attacker extracts the secret decryption key within seconds from a target located in an adjacent room across a wall. So this is kind of a dangerous side channel. So for military equipment, they usually use hardware crypto instead of software crypto because of these kinds of things. We have something called authenticated encryption, and with authenticated encryption, we actually get integrity included. So we can get both confidentiality and authentication. What we're doing then is we add like a message authentication code or an authentication tag as a part of the encryption. And some common examples of this are AES in GCM mode or CCM mode. And GCM and CCM mode, they're both based on something called counter mode. And counter mode works like this. So we have our plaintext once again, and we have this nonce. And we're going to do something weird. Instead of encrypting the plaintext, we're going to take this nonce, and we're going to use it as a counter, hence the name counter mode. So we add a counter to each of these blocks. And then we're actually going to encrypt these counter blocks using the encryption function, which could be AES, for instance. And out of that, we get a key stream. And then we can actually XOR our plaintext with that key stream to get the ciphertext. So we're kind of creating a stream cipher from a block cipher in this case. And we have to use the nonce when we want to decrypt it as well. But the weird thing here is when we want to decrypt something, we're still going to use the encryption function because we need to get the same key stream that we had earlier. Because we're not actually encrypting the ciphertext, we're encrypting the counter blocks and then using that to encrypt the plaintext. So once again, we create the key stream and we can truncate the parts of the key stream that we don't need, and we XOR together to get the plaintext. So this is what it actually looks like for GCM. What you see in the top right corner with the blocks up there, that's the counter mode stuff. And then there's something else going on down here on the side, which is creating this authentication tag, which gives integrity as well. But the problem with GCM and CCM is we can only use the nonce once. If we use the same nonce and the same key, we get the same key stream. Hence, we're back to the problem that we had with the one-time path. If we have the same key stream and we have XOR something with it and we XOR two ciphertext together, we get the XOR of the plaintext blocks. And this was found to be a problem in a lot of different devices that were using GCM on HTTPS because they would repeat the nonce at certain intervals. Like if you rebooted the device, it would start up with a fresh thing and it would repeat. So actually, if we're using this mode, we need to ensure that we never use the same nonce. And if we've used up all the nonces, then we actually have to replace the key, which is something we should do, but that's not immediately clear to everyone. If we're going to do asymmetric encryption with something like RSA or elliptic curve, we have, at least for RSA, we have the same limitation as we had for one-time pads, that the message length actually has to be smaller than the key length. So what we normally do with something we usually call hybrid encryption is, instead of encrypting the data using the asymmetric algorithm, we generate a symmetric key, we encrypt the data with that one, and then we just encrypt this symmetric key using the asymmetric algorithm, and we send the encrypted data and the encrypted key over to the other side. So this is what happens on HTTPS. If you're going to use RSA, it comes in some different kinds of modes. Something called RSA OAEP, that's the recommended one, but there's something called PKCS1 version 1.5 padding, which is also kind of broken. So Matthew Green, who's a crypto professor in the US, he says that PKCS1 version 1.5 is awesome if you're teaching a class on how to attack cryptographic protocols. In all other circumstances, it sucks. So if we can actually have a padding order just like we had for CBC mode, we can have that for RSA as well. So the way that we pad a message with when we're using RSA is we add a 0 byte, and then we add a value of 2, and then we have some random padding bytes, and then once again a 0 byte, and then the actual plain text. And the way we encrypt stuff using RSA is we have a public exponent E, and we raise the message to the power of this exponent, and then we take modulus N, which is a part of the key. I'm not going to go into the details of this. And when we want to decrypt it, we raise it to the power of the private key, which is the exponent D instead. The problem in this case is with the way modulus works is if we multiply the message that has been encrypted with some other integer s, which we also raise to the power of the same public exponent, it can't really determine if they were first both raised to the exponent or if they were multiplied together and then raised to the exponent. So we can actually multiply a ciphertext that we don't know the contents of. We can multiply it with an integer s raised to the power of e and send it to the server, and the server will think that this was actually done in advance, that this s was multiplied with m before it was encrypted. And if it now leaks the fact that the padding was correct or not, we can use this to attack it. We know that all the valid messages, because of the padding here, is going to start with 002, and they have to be less than 003. So there's a span of valid messages. And I've tried to figure out a way to visualize this, because it's kind of hard to explain this algorithm. But I've found one way that might work. But a guy called Daniel Bleichenbacher, he figured out this in 1998, that this way of padding was vulnerable, with something called the million message attack, which was then later improved upon in 2012, where you could do the million message attack in 15,000 messages. So the name the million message attack is because you need to send a lot of messages to the server to try to break it. But to try to visualize this, we can imagine modulus as a circle, which is not really all that visible here. But anyway, you have the sector here, the yellow sector. That's the set of valid paddings. And on the left-hand side, we have a message at the start of the valid padding, and on the right-hand side, we have this green stripe here. That's the green line. We have a message at the end of the valid paddings. So we can think of modulus as a clock, because when we get to 12 o'clock, it kind of wraps around, and the same thing holds for modulus. So if we take the ciphertext and we multiply it by some integer s, the first time we do this, we're going to hit outside of the valid padding. So we're going to get a padding error back. But if we do this enough times, at some point, we're going to hit a message that actually has a valid padding. And now we can go back and calculate what that means for the original value, which we don't know. Like in this case, we got a valid padding at an early stage, which means that we probably were towards the end of the padding spectrum. But we can calculate this. So we can calculate now a range of possible values that could give us this. On the left-hand side, we see we still haven't reached a valid padding yet. But at some point, we're going to reach it. And then we're narrowing down the ranges of these messages. So in this case, I have a huge sector, but if this was actually RSA, it would be so small that we couldn't see it. But we can do this, and it will keep narrowing down the possible values. And at some point, we're going to be left with only one possible value. And at that point, we've found the value. Of course, this was in 103 and not a million, because I had a huge sector and a tiny n. But in an actual scenario, you'd have to send a million messages. But I'm not going to let you sit here and watch me click a button a million times. That would be kind of boring. So this is kind of a way we can, by sending a lot of messages, we can calculate what the original message was, and that's how the way the algorithm that was invented by Bleichenbacher, that's the way it works. Daniel Bleichenbacher, he now works for Google, I think, making like crypto verification tools, which is kind of awesome because he's one of the inventors of many attacks on crypto. So if we're not going to use GCM, we could use something called encrypt then sign, which basically means we take our plain text, we encrypt it, and we get the ciphertext, and then we sign the ciphertext, and we send that off to the server, and then the server will first verify the signature and then decrypt the plain text. And it's important that we do this in the correct order, so we don't reintroduce the padding oracle. But we could actually use this with CBC, and it would be safe as long as we always check the signature first. So signing. We've now looked at encryption, and we've looked at some attempts of using encryption in the wrong way, where we tried to do signing with encryption and it didn't really hold. So how do we actually sign stuff? Well, a lot of people have tried to invent their own signing as well. So they've done stuff like this. So we take MD5 of a secret and then the message we want to sign, and we calculate a hash from that. And we think that that's safe. And the same thing is if it was SHA-256, it doesn't really matter which of these hash functions we use. It's still broken. And also if we put the secret at the end, that's still not something that we can do because it's broken. An example of this was Flickr. They had an API signature back in 2009, and there were a couple of researchers that found this flaw. So what Flickr would do, they would allow us to sign URLs. And so in this case, we had these URL parameters. And the way that they would do the MD5 was they would take a secret, and then they would take the URL parameters, and they would remove the ampersands and the equal signs and just stick that at the end, which was kind of a weird idea because that means you can't separate between the top one and the lowest one here. They're going to be the same. But because MD5 with secret plus data is vulnerable to something called length extension, it means that we can add data to the end. And this is where the problem comes in, because now we can add some stuff to the beginning, which is a parameter that we're not really using, and then we can add new values for these parameters that we had to begin with. So we can extend a valid signature to now be valid for completely different data than what we expected. So this is broken. Never do this. There's a reason why we have something called HMAC, and that's because these are secure constructs, and these are done in the right way. If we're going to sign with a private key, this is something we can do that also provides identification. So we can sign a token, and that proves that we are who we claim we are. For instance, we could use something called RSA PSS, probabilistic signature scheme, or we could use elliptic curve, but we should not use this PKCS5, PKCS1 version 1.5 here either, because we can use the same padding vulnerability to forge signatures. XML is interesting as well. With XML, we introduced this large chunk of XML as a part of a signature. So if we have this SSO token in this case, we have a username with an ID, and the username is Homer Simpson, and we have this login time that's in here. So we're going to add an XML signature to this. We first add a signature element. We then add something called signed info. And signed info basically says what part of this XML is signed. And we bring in something called the canonicalization method and the signature method. So the canonicalization method, it tells us how we should transform the XML before we sign it. And the signature method in this case says that we're going to use RSA and we're going to use SHA-1. And then the references. The references are what is actually signed. So in this case, we have something that starts with a hash and then _0. So that points to something with the ID _0, which in this case is this element, because this has this ID. So the underscore 0 with a hash in front, that points to this element. So this is the only element in this XML that we're going to sign. And this is the flexibility of XML signatures. We can sign individual elements. We can pick and choose which elements we want to sign. But this is also one of the big problems with it. But again, for this reference, we add a canonicalization. Here it's called a transform, but it's the same function that we used above. And we're going to say how are we going to canonicalize this XML, and then we add a hash for that token. So the reason why the canonicalization methods are important is that XML can be in many different forms. Like we can have self-closing tags, we can have an open and close tags, and we can have all sorts of stuff. So by using a canonicalization method, we ensure that they are always on the same format before we calculate the hash. Now, once we've done this, what we're going to sign is actually not the thing that's on the top there. We're actually going to sign this signed info element. So this part is what we're actually signing with this signing method that's here. And the signature values then actually covers the signed info element, which is kind of odd because we're then hashing something and then we're adding that to something and then we're hashing that and signing that again. So it's kind of a double hashing thing going on there. So if we're going to validate this XML signature, well, we could do a lot of things wrong. So first part here, what's wrong with this code? Well, we're trying to validate a token. So we bring in an XML document and we convert it into a signed XML, or wrap it in a signed XML element, and we pick out all the signatures because we could have many, and we validate them. And if one of them fails, we're going to throw a security exception. Now the problem in this case is, what if there are no signatures? Well, it's going to just skip the for loop. And this sounds stupid, but we'll get to it. So we're going to fix it. Like we're going to add, even with an angry comment here, we need to check that there's at least one signature. So in this case, we're going to check that there's at least one signature. We're going to validate all the signatures that we find, and then we're going to grab, using XPath, we're going to grab this, this part here. So SSO token / username, that's going to be this part. That's what we want from this. The problem in this case is, are we using the thing that was signed? What happens if we move the element that was signed? So in this case, we took the username element that was signed and we moved it under some random other element called ignore me, and then we added a new username here. And this is still going to validate the signature because the reference down here, it says I'm going to find something with an ID of _0. Well, that's up here. And I'm going to calculate the hash of this. Well, this hash here, it's the correct hash. And then I'm going to check that the signature of this matches whatever is provided down here, and it matches. So the problem is we still have something that's signed, but we've moved the thing that was signed. And I'm going to show you a quick demo of this because it's kind of funny. So we have, in this case, we have a token that we can post to a server. And we have somehow managed to get hold of an expired token. So if we try to send that to the server, it's just going to say error, expired token. So we're going to look at this XML, and it looks something like this, which is kind of hard to read. So I'm going to help us a little bit out here. So we have something at the top that's an SSO token. We have obviously some kind of a date here, which is probably why it was expired, because this is a month ago. And we have the signature, and we have this piece here at the end. So what we can do now is we can move this a little bit. So we take a copy of this, and we take a copy of this, because that's what's actually been signed. In this case, if we look at the reference, which is here, we see that what was signed was the entire token, not just the username. So for our newly forged token, we're going to remove the ID of the top level element, because the signature, it's on this element down here. And then we're going to change the username to something different, like this. So now we have a signature that's over this element, but we're hoping that the system would instead use the outer element. So we've wrapped the signature. And we forgot to change the date. So we're just going to do 2019 because why not? And now I'm the admin. Like I've just forged a signature here. And this sounds kind of odd. So missing signatures and wrapped signatures, that can't be a real problem, right? Well, it can, because someone did a survey on SAML validation libraries. And SAML is SSO token libraries, basically. So, and they found that out of the 14 major SAML frameworks, 11 of them, including Salesforce and IBM, had critical XML signature wrapping vulnerabilities. And for some of these libraries, you can even just remove the signature and they would still validate. So you could be, so then the name of the paper is be whoever you want to be, because you could just forge the tokens. So moving on, if we want to validate a signature, we could do something like this. So we're going to bring in the signature, we're going to check that they have the same length, and if they don't have the same length, we're going to return false. And if not, we're going to move into this for loop where we check one char at a time, basically what an equals function would normally do. And then if we find something that's different, we're going to return false. We're going to return early, that's the thing here. And if not, we're going to return true. So in this case, of course, we have a timing problem, because if it returns early, it means that the mismatch in the signature was early. So we can try a lot of different values, and we can measure the time, and we can use this side channel to figure out what the correct signature should have been. And we can try to fix it. So we could do something like this. So instead of returning early, we have a Boolean, and we set result equals true. And then if it finds something that's different, we set result equals false, and then we return the result. The problem in this case is we have something called JIT. And JIT is going to figure out that we're setting it to true up there, we're setting it to false down there, and there's no way it can be reset back to true. And there are no side effects, so the JIT can just skip the rest of the comparisons, because now we have set a result to false, and it's never going to be reset to true. And again, we have the timing problem. So what we need to do is use something called a constant time comparison function, and this is usually provided by the framework, so you don't have to actually implement this code. But what we're doing here is some XOR and OR stuff to make sure that it doesn't get fixed by JIT. So if we're going to validate signatures, what we want to do is we want to verify the signature. We want to verify that the elements we expect to be signed are in fact signed, and we want to verify that the elements that we expect to be signed are signed in the way that we expect. So they're not signed with a different function, they're not signed in a different way. And then we have to make sure that we're actually using the data that was signed. So in the wrapping examples, we saw that we didn't actually use the data that was signed, we just moved that elsewhere. So I'm going to end off with some examples from JOT, or JSON Web Tokens, because there's a lot of stuff that has gone wrong there lately. So a JSON Web Token looks something like you see at the top there. So the first part in red, that's the header, which tells us which function was used. In this case, HS256, that's HMAC SHA-256. And the green part, that's the claims. So in this case, we have a subject with the name of Homer, and we have a timestamp when this was created. And then we have the signature in blue, which is created by base64 URL encoding the header, and then adding a dot, and then base64 URL encoding the payload, and then signing that with the signing key using the method that's specified in the header. So implementation issue number 1. Forgetting to check the signature when we're verifying the token. This is quite an easy thing to miss, actually, because a lot of time people will do something like this. They will have some kind of JVT library, and they will call the decode function. And they will think that it actually verifies the token as well, but it doesn't. It just decodes it and brings you the data from the payload, but it doesn't actually check the signature. Implementation issue number 2. If we go to the RFC, at the bottom there's something odd. There is an algorithm that we can use in the header that's called none. And none basically means, as it says in the center there, no digital signature or MAC performed. So we actually have a token that's unsigned. And this was actually supported by a lot of frameworks. So we could take a valid token, we could remove the signature, we could change the algorithm to none, and then we could change the payload, and we could once again become whoever we want to be. Implementation issue 3. Once again, we look at the RFC, and we see this stuff. And we already know that PKCS1 version 1.5 has some issues. For some reason, it's been included in the RFC for JSON Web Tokens. And here's an example. As you can see here, it says, for this library, JW Crypto, the implementation of the RSA1_5 algorithm was found to be vulnerable to the million message attack, which was the one we talked about earlier. Implementation issue number 4. We're reading in some key bytes from a file, and then we're going to verify a token that we're getting in. And in this case, it was supposed to be signed asymmetrically. And the public key is, of course, something that anyone can download, because anyone that's going to use these tokens, they are supposed to be able to verify that these tokens were signed by the entity that was supposed to sign them. So they can all access the public key, but of course they don't have the private key. But what an attacker can do then, if this is implemented in a wrong way, he can take a token that's signed asymmetrically and then change it to be signed symmetrically, and then fool this algorithm on the top here to think that the public key is an HMAC key instead, and the public key is known. So now you can forge a token by pretending that it was a symmetric token instead of an asymmetric token. And a lot of libraries actually were vulnerable to this, because they were doing something similar to what's written at the top here. So they would read some key material from a file, and then they wouldn't care if that was an asymmetric key or an HMAC key, and they would just use it. And just use whatever came from the token to figure out how it was signed. So implementation issue number 5, weak RSA keys. So we have weak randoms. Some people think that, well, our tokens are so long, so we're going to use a shorter key because that makes the token smaller. But if you use a 512-bit RSA key, you can trivially break it for $75 on AWS. And a 768-bit RSA key is also not recommended anymore. It's also something you can break in a quite short time. We could also have a weak HMAC key, which is just a short text string. That I see a lot of developers doing this. They bring in this short text string, and then that's their HMAC key. And actually now Hashcat has support for JSON Web Tokens. So that makes it a lot easier to try to break them. So we can have a file with some JSON Web Tokens, and we try to brute force the HMAC key in an easy way. Implementation issue number 6, using standard equals functionality in the programming language, which means we probably might get a timing side channel because it might exit early. And implementation issue number 7, wrong comparison. So in this case, we calculate the HMAC, and then we're going to try to use like a timing safe equals function here, but we're using the wrong length. So instead of using the expected signature length, we're using the signature that we're getting in from the attacker. We're using that length. And this was actually a problem that was in the identity model extension. And like this blog post didn't really say all that much, but on Twitter I found an explanation of what was wrong here. If we scroll all the way down, it says, which means you can truncate the JWT signature to force the comparison on the first byte only, a real disaster. So you could just remove the entire signature except for 1 byte, and then you could just brute force it. It would be like with the NQ vault, like there would be only 256 different possible values. So some recommendations towards the end here. Never ever invent your own crypto or signing. Use cryptographically secure randoms. Use vetted crypto. So if you're using .NET, use data protection. If you're going to use something else, use properly tested crypto libraries, and preferably ones where you don't have to add all kinds of stuff manually. Do not put the keys in source control, as we saw. There is a really good presentation called Everything You Need to Know About Cryptography in 1 Hour from a guy called Colin Percival, which is actually more than 1 hour, but still a good talk. And some recommended people you could follow. There's Matthew Green, which I mentioned with the PKCS1 examples. And then there's a really good book called Cryptography Engineering, Design Principles and Practical Applications, which is, among others, written by Bruce Schneier. But if you really want to learn this stuff, you should, oh, it's missing here, sorry. There's a really great website that's called the CryptoPulse Crypto Challenges. And this is a set there are 8 sets of tasks, And each set has a set of tasks that you can do here. So you have, for the first set, you have 8 different things that you can do. And by doing these things, you learn all this stuff, like how to break XOR or one-time paths, and how to break RSA, and how to break CBC and things like that. So they're really great. And you can find solutions for them. You can write your solutions in any programming language, and you can find solutions in a lot of different programming languages if you're stuck. If you're going to do this, I really recommend that you follow the instructions, because there are some really good recommendations on how you should write your code so it can be reused. And I didn't quite follow them the first time I did this, and it was really annoying later, because you're going to write bits of code and going to reuse that code later, and it gets really annoying if you do it the wrong way. Yeah, that's it. Any questions? So if you didn't understand some of the attacks here, don't feel bad. I had to read this stuff many, many times to understand, like the padding oracle stuff. It's super hard to understand, and it annoyed me for such a long time that I eventually went back and read it enough times to understand how it works. So if it's kind of mind-bending, don't worry. And if you have this, if you're like me and you really want to understand it at some point, you're going to understand it eventually. Yes?
Just thank you for the visual presentations. It made it a lot easier to understand. I just wonder if you know, for the couple of the issues that you had, the bugs that you found in the cryptography, do you know if there was any unit tests for that?
If there was any unit tests for these libraries, I'm not sure.
Yeah,
No.
some of the bugs, the one with the signature that was getting lost in talking, for example. That should probably be very easy to be picked up by a unit test.
It should be, but you have to know about it, and that's the problem. A lot of that's kind of the reason why I'm doing this talk, is I want people to be aware of these things, because it's easy to get it wrong. And if you don't know that, you could, like in an XML, you could move the signed token somewhere else, and then it would still validate. You wouldn't think of adding a unit test for it.
And unit tests usually cover good cases,
Yeah.
the right cases, but not the wrong cases.
True.
Infinitely more, infinite number of infinite cases, and only maybe one correct.
Yeah, very often unit tests only cover the happy paths, which is also a thing that we should change. We should start adding unit tests that actually test unexpected behavior or stuff that we don't want to happen, like signature wrapping, like signature truncation, and things like that.
Yeah, or if you start with tests rather than code, maybe it's fine with that.
Yeah, another question.
Mm.
So there is web crypto being done to the browsers now.
Mm.
So which will encourage people to use crypto in JavaScript.
Mm.
And JavaScript has all set of problems.
Mm.
So is there any research or anything about using web crypto in browsers and typical issues which people face with it?
The stuff that I've seen so far is people using math random from JavaScript. That's the only thing I've seen so far, because now in all browsers you can do, let's see here, I'll just move to the other one. Oh, sorry. Browsers now usually have something called window.crypto.
Crypto, yeah, definitely.
And in there you actually have functions for doing like get random values. So you have a secure random right in there. So you don't have to use math random and get stupid random. You actually have proper random in the browser now. And so they're probably going to add a lot more stuff there, like hashing functions and cryptographic functions and things like that eventually. But there isn't all that much there at the moment. There are some implementations, though, of cryptographic libraries for JavaScript. I know Stanford has some. And, so you have to pick the ones that are vetted if you're going to do it, and hopefully it will get included in the browsers eventually natively. But I haven't been following the progress there. So, yes?
Is there a good resource for checking which libraries have been implemented? Or is it just a case of having an eye on
So the libraries that come out of Google, they've been subject to Bleichenbacher's test tools, so they're usually good. The stuff that it's in the .NET framework is I would suspect now is properly tested, even though they've had some bugs earlier. So I think as long as you stick to something that's from a or that has been tested through, you could probably find pieces of it in the source code if it's been tested with a proper testing library that actually checks for these things. There might be unit tests or integration tests or things like that that actually test it. I think I've seen some recommended libraries. In Java, you usually use like Bouncy Castle, because that's been tested a lot. In the .NET space, you usually use the built-in stuff because the .NET framework has AES and all kinds of cryptographic libraries in there, which are probably implemented correctly. If you're on Node or some other platform, then I don't know. All right. Thank you.